Initially, an interest was taken in Blue Origin's proposed orbital reef, a commercial space station which uses inflatable modules designed by Sierra Space. The modules allow for larger volumes of usable interior space compared with cramped conditions of the current International Space Station. Multiple inflatable modules can be transported from Earth due to their low weights compared to conventional aluminium modules, making space construction more cost-effective than ever before. Although the station uses new technologies and inflatable structures, it still uses notions of earthbound design in relation to gravity. The clearly defined walls, floors, and ceilings have no use in outer space. The project will propose an orbital space station situated in Earth's thermosphere. This will provide habitation for a self-sustaining nomadic community in space. The station will have a central core containing research, development, and manufacturing facilities for the production of organic fibers. These fibers will be robotically assembled into inflatable structures, enabling a complete construction of the proposal in space. The continuous production of the station's construction material will allow its growth and reconfiguration to be based on the community's needs. On Earth, inflatable transport originated with the Zeppelin in the 1900s, which comprised of inflatable compartments filled with helium gas. Although the size of the Zeppelin was over 200 meters long, the inflatable part of the airship was only 5% of this size, leaving a huge disparity between the usable and wasted volume. In the 1970s, Ant Farm explored the use of inflatable architecture, which, like the Zeppelin, had a very little usable space compared with its volume. However, the experience of the space provided new insights into how humans could interact inside and on top of inflatables. More recently, Thomas Saraceno has designed inflatable membranes that deform to engulf those that walk above and below. This gives the users a tactile experience as they move through the membranes. NASA first explored inflatable space architecture with the Transhab, which was designed in the 1990s as a replacement to the ISS habitation modules. Due to cost and technological restrictions of the time, the project was never realized. However, the lessons learned from its development have been applied by the likes of Blue Origin, Sierra Space, and Bigelow Aerospace, all of which are now developing space inflatables. Like the orbital reef, the interior architecture fails to consider life in zero-G. Floors and walls only offer privacy between programmatic elements of the proposal, making horizontal floor planes redundant in space where orientation becomes nebulous. By analysing the deployment of the Transhab from the Orbiter space shuttle, it is clear that even when in space, the predetermined orientation of the internal architecture affects how it is removed from the orbiter in its supposed upright position. After the Transhab has been deployed, compressed air is pumped into the main space, inflating the external envelope. To do this safely, the crews stay in the pressurized cabin until the envelope has been fully inflated. Once this has been achieved, the crew can take modular floor panels and shelving and reconfigure the internal space to the new internal volume. The Sierra Space proposal, which is currently in development, is almost identical to the Transhab. Sierra Space, however, plans to stow the whole inflatable in the pressurized cabin, reducing the volume and weight that needs to be transported into space. Another difference is the materials used for the inflatable. The Transhab used more than 30 layers of different fabrics to protect from space debris, radiation, and low temperatures. Sierra Space uses Vectron fiber, which needs fewer layers due to its strength and insulative properties. Although Vectron fiber weave is strong, it is difficult to manufacture, as it can only be created by spinning liquid crystal polymer in a chemical reaction. An organic alternative may be spider silk, which can be artificially produced using hydrogels to create fibers. Golden orb weaver silk is tougher and performs better under stress than steel, Kevlar, or carbon fiber, making it ideal for use in space. The diving bell spider uses a combination of hydrogel and sheets of silk to inflate air bubbles below the water's surface, which it uses for breathing and as shelter from predators. The hydrogel silk combination allows the diffusion of gases in and out of the bubble, so that carbon dioxide exhaled by the spider can leave and nitrogen can enter. This prolongs the time the spider can stay in the bubble without replacing the air. Another interesting property of the diving bell spider is its ability to weave three-dimensional webs regardless of its orientation. The only parameters the spider needs are connection points to anchor its web. This could provide precedent on how to design for humans without gravity. To understand the diving bell's web structure in more detail, the different typologies were microscopically analysed. There are three main types of fibre produced by the spider, which are used for different parts of the web based on the structural and spatial conditions. Sheet web A comprises of thin structural fibres and a hydrogel mucus. Sheet web B has significantly thicker threads, which are also interconnected with hydrogel mucus. The wall of the diving bell interweaves thin fibres to produce stronger, larger strands. Initial tests explore the connections between moving fibres and how they can glue and stretch under stress, like that of the diving bell web. The next test explores how the web can form 3D connections in space and hang between these connectors. The evolution of this is forming connections between an object and the connectors in order to support the object. Moving forward with the design proposal, the 3 web typologies identified with the diving bell web spider will be explored as an aid to locomotion and orientation in space interiors. The materiality of the web will also be explored with the artificial manufacturing facility, which will need to be transported from Earth. Once this has been established, the production of artificial spider silk can begin. These will enable the inflatable parts of the proposal to be produced in space.